Hello, my name is Victor from Huawei Noah's Arc Lab. Today I'm going to present our work, namely on nearby fit spatial keyword queries. Here is outline. I will give an introduction first and then formally define the problem and present the proposed algorithm and the experiments. Finally, I will conclude the work and propose several research directions in the future. Nowadays, the geolocation data is ubiquitous. Many apps and web pages allow people to give comments for each point interest they visit and thus, each point of interest not only has a location, also has a set of related keywords. Consider the example as shown in the figure. There are 8 point interests, and each square point interest has a keyword hotel. Each diamond point interest has a keyword convenience store, and each trapezoid point interest has a keyword cafe. Each triangle point interest has a keyword pub, and each round point interest has a keyword hotel and a cafe. Now, Tom is going to attend an international conference and would like to find a hotel such that the location of the hotel is near to the conference venue marked by the black dot in the figure. And secondly, there were at least a convenience store, a cafe, and a pub nearby the hotel. Although there were many existing works on the spatial keyword queries, none of them could find the desired result for Tom. In the following, we will describe how existing queries could not find the good hotel we want. There were A, spatial keyword KNN queries, B, collective spatial keyword queries, co-SQQ in short, C, M-closest keyword queries, MCK in short. The first highly related work is spatial keyword KN queries. In our case, K is equal to 1 and it simply finds a nearby nearest point interest containing the keyword hotel, which is H3. But the vicinity of H3 is almost empty. So another highly related work is co-SQQ, which finds a set of point interests which collectively cover hotel, convenience store, pub, cafe, and their distances to the query location is the smallest. In our case, it returns H1, S1, P1, and H1 is the object containing the keyword hotel. The problem of H1 is that H1 is far from the conference venue, which will bring inconvenience to Tom. The third one is called M-closest keyword query, which finds a set of point interests which collectively cover a hotel, convenience store, pub, cafe, and their maximum pairwise distance is the smallest. Thus, it is not aware of the query location. In our example, it also finds H1, S1, P1, and H1 is point interest containing the keyword, but is far away from the conference venue. We illustrated the inefficiency of existing queries. We next show our preferred solution called nearby fit spatial keyword queries. So in this query, H2 is a preferred solution because H2 is very close to the conference venue and it has a pub, a convenience store, and a cafe in its vicinity. So the contribution in this work is as follows. We propose a new query called nearby fit spatial keyword queries. We prove the problem is NP-hard and propose 2 approximate algorithms. We conduct experiments on real and synthetic data sets and verify the efficiency and effectiveness of our algorithm. Now let's go to the problem statement. So in NSKQ, we call the keyword that the desired object should contain the target keyword. And we call all the keywords that nearby object should cover the nearby keywords. So in the hotel finding problem, the target keyword is hotel and nearby keywords are convenience store, cafe, and pub. So let's first define a cost, namely small o given Q and big O first. So give a query with a query location and a target keyword and a set of nearby keywords. An object O with the target keyword and a set of a big O of objects covering all nearby keywords. We have the cost of small o given Q and big O to be alpha times DOQ and plus 1 minus alpha times the maximum pairwise distance between the objects in big O. So in this example, let's consider H1 and its nearby objects S1 and P1, and H2 and its nearby objects C2, S2, and P2. So the red line denotes the distance between the const value and each hotel considered. And the purple lines denotes the maximum pairwise distance in each of the nearby objects. So we can calculate the cost of H1 given Q and S1 P1 is equal to 2.6. And the cost of H2 given Q and S2 P2 C2 is equal to 1.85. Now let's present the cost of a given object containing a target keyword. So given a query containing a location, a target keyword, and a set of nearby keywords, and an object O with a target keyword, we have the cost of small o given Q is equal to the minimum of the cost of small o given Q and big O, that big O covers all nearby keywords. So in this example, we can calculate the cost of H1 given Q is equal to the cost given the cost of H1 given Q and S1 P1, which is equal to 2.6, and the cost of H2 given Q is equal to the cost of H2 given Q and S2 P2 C2, which is equal to 1.85. Thus, the optimal solution is H2. Now we're ready to define our problem. So given a query containing a location and target keyword and a set of nearby keywords, the problem is to find the object O containing the target keyword with the minimum cost of O given Q. We prove the problem is NP-hard. And our experiments show that any exact algorithm either developed by us or adapted takes more than 1 hour on a sizable data set. So due to the real-time requirement of NSQQ, we only focus on development of approximate algorithm with polynomial time complexity in this work. So now let me show the comparison of our algorithm and baselines in terms of accuracy and the time complexities. So in this table, a small n is the number of point entries. And the algorithm in the red box was originally designed, was adapted from the algorithms for co-SQQ. And the algorithm in the blue box is the algorithms adapted from the algorithm for MCK. So as you can see in the table, and they either have a very big time complexity, which is larger than n squared, or a very large approximate ratio, which is larger than 2. And the two algorithms in the green box is our algorithms. As you can see, they both have a time complexity smaller than n squared and approximation ratio which is smaller than 2. Now let me present our proposed algorithms. So in this work, we propose 2 approximate algorithms. And here n is the number of point entries and m is the number of nearby keywords. And m is typically smaller than 10 in our real-world applications. So the rationale of this assumption is that user won't input too many keywords in a search. So the running time of our algorithm 1 is big O m cubed n log n, and the approximation ratio is 1.15. And our algorithm 2 takes big O m n log n plus n log n square time, and its approximation ratio is 1.779. So let me present our algorithm 1. So first, let me present a key concept, covering disk. A disk theta is called covering disk if the object contained in it cover all the nearby keywords and the target keywords. So in this example, there are 9 objects and 3 disks. And the target object, the target keyword is C, and the nearby keywords are A and B. In this example, theta 1, theta 2, theta 3 are all covering disks, since there exists a set of objects in each disk, which covers all the nearby keywords and target keyword. So let me present the second key concept, minimal covering disk. A disk theta is called a minimal covering disk. If first, it is a covering disk, and secondly, there does not exist a smaller covering disk, which does not contain any object outside theta. So in this example, theta 2 and theta 3 are both minimal covering disks. Since they are both covering disks, and there does not exist a smaller covering disk, which does not contain any object outside the disk. And theta 1 is a covering disk, but not a minimal covering disk, since there exists a smaller covering disk, theta 3, which does not contain any object outside theta 1. So our algorithm 1 enumerates each minimal covering disk, and in each disk considered, it finds the nearest object O to Q containing the target keyword, and finds a set big O of objects covering all the nearby keywords. And it computes the value of the cost of small o given Q and big O. And so in this example, consider theta 3. The nearest object in the disk to Q containing the target keyword C is O3. And the nearby objects found in our algorithm is O1, O2. And finally, the algorithm returns the object with smallest estimated cost containing the target keyword. And the approximate ratio is 1.15. Now, let me present algorithm 2. So let me introduce two key concepts first. So let's consider an object containing the target keyword. So its center-centric nearest neighbor set of the object O is a union of the nearest neighbor of O containing the keyword T for each T in the nearby keywords. So here, the NNOT denotes the nearest object to O containing the keyword T. And this concept is computationally cheaper than the minimum covering disk, but it introduces large error. So thus, we introduce another concept called minimum covering axis parallel square. So the minimum covering axis parallel square is the smallest axis parallel square, such that the object in which collectively cover all nearby keywords and target keyword. So consider the example. Let's consider O9, which containing the target keyword C. So its center-centric nearest neighbor set consists of O7 and O8. So in the right figure, and the two square Q1 and Q2 are both minimum covering axis parallel squares, because the object in each of the square cover all nearby keywords and the target keyword. So in algorithm 2, we first find the center-centric nearest neighbor set O for each object O containing the target keyword and estimate the cost of O given Q and big O. And then we find the minimum covering axis parallel square by using an existing algorithm, and find the nearest object O to Q containing the target keyword and set of big O of objects in the square covering all nearby keywords, and estimate the cost O given Q and big O. And finally, return the target object considered with the smallest estimated cost. And the approximation ratio of this algorithm is 1.79. Now let me present experiment. So in the experiment, we conduct experiments on the web, GN, and hotel data sets, and we tested our algorithms and all adapted algorithms. So this figure shows the trade-off between accuracy and efficiency on web data set for all algorithms. So for the better clarity, in the results shown later, we only consider the 4 algorithms on the skyline. So the figure shows that our algorithms are the most accurate, and it is the second and third farthest. And in this paper, we propose a problem called nearby fit spatial keyword queries, and we propose 2 approximate algorithms. And in the future, we will consider the variance of the NSKQ. Thank you.